Point-to-point protocol. The point-to-point protocol was designed to support a multi-vendor, wide-area network environment with dedicated links between two endpoints. Before the development of PPP, a point-to-point link had to have devices from a common vendor on each end. In this nugget, we're going to start by looking at the PPP placement among WAN protocols and define the one command needed for basic configuration. Also, we're going to list the components involved in the point-to-point protocol. In the last 4 sections, we're going to look at the different phases of the PPP model, starting with link control protocol. Then we're going to look at the authentication options, the network core protocols that are supported under PPP, and we're going to end up with a discussion on the encapsulation. Before we can define PPP's place among WAN protocols, we first need to understand what we're talking about when we say wide area network protocols. I'm going to start off with this model here of this router. What I have is 2 interfaces. One is Ether 0, the other is Serial 0. Now we know so far that if we make a connection to this interface and have a series of PCs out here, this connection and the environment that we create out here is called a local area network, okay? So this is the difference then. A WAN environment is simply that same concept, except it's applied to a serial interface, okay? Because these are designed for long distance, in other words, the wide area rather than the local area. All right, so if I make a connection here with a serial interface connected to another device, this entity that we've just created is a wide area network, and that's what we're dealing with now in defining protocols under that WAN. Now let's look at the OSI model and understand which layer we're dealing with as far as protocols being defined under a WAN. Right here at the data link, we have the bottom layer, which is the physical layer where the bits and bytes reside. The data link layer is what we're dealing with, and above that is the network layer where we have the protocols that are defined like IP or IPX. Layer 2 WAN protocols can be divided into 2 distinct groups, the first of which is the group that supports point-to-point connectivity only. This is the only type of connectivity they'll support. Let me explain what I mean by that. I can have a router here, a serial link out of that router connected to an endpoint of another router. Understand that there are only 2 endpoints on this connection, and that's why it's called point-to-point. 2 of the most common protocols that are assigned to support this type of connectivity, first, HDLC, stands for High-Level Data Link Control, and then we also have the protocol we're studying today, PPP, or Point-to-Point Protocol. The second category of WAN protocols at the data link layer is considered multi-point. Don't get confused though. We're not saying that it doesn't support point-to-point connectivity. In fact, what we're saying is it supports point-to-point connectivity as well as point-to-multi-point. In other words, if we had another device in this environment connected here. Now the multi-point protocols that are common, the first, frame relay, which we're going to study extensively within this series. We also have the packet switching, known as X.25 protocol, and then we have ATM, which is asynchronous transfer mode. It's a cell-based transfer mode used for point-to-multipoint connectivity. So as you can see, HDLC and PPP exist within the same category to support the point-to-point connectivity. So let's talk about how they're different. First of all, again, the high-level data link control. The problem with high-level data link control is that it is vendor-specific. It wasn't designed in its initial phase to be a standard throughout the whole industry. In fact, let's look at exactly what we're talking about. It has proprietary information. In the case of Cisco, when I am looking at a frame that supports HDLC, a portion of that frame, in this case the type field, is proprietary to Cisco, and it's how they are able to support multiple protocols. All right, so if I have a Cisco device here and a Cisco device here using HDLC, I can make that connectivity and they can speak to each other. But if I have a Cisco device here and some other company's device here, I'm not going to be able to make this connection, okay? It's going to break down because of this proprietary field. In fact, this problem existed in all WAN protocols that supported the data link layer before PPP was developed. None of them could interoperate well between different vendor devices. So along came PPP, and it was designed to overcome that hurdle. And what they said is, let's make a standard frame that supports the data link layer so that I can make connections between like devices and also unlike devices. So PPP will do that for you. But beware, when you are configuring a Cisco device, HDLC is the default protocol defined for encapsulation on serial interfaces. It's not hard to change the encapsulation type. Just be aware that the default is HDLC. And as luck would have it, we're going to show you the command to change that encapsulation type right now. What we have here is host name and the number sign. Please recall that that is the privilege level of our router. We're going to assign the command config from terminal so that we can get into the configuration mode as identified here by the prompt. Once we're in there, we're going to configure an interface. In this case, interface serial 0, and it's going to change the command to config IF. Okay, that should all be review. Now, the command we need to activate PPP, the basic operation, is encapsulation space PPP. This is where we would have the options of different types of encapsulation. In fact, one of the options under this encapsulation command is HDLC. These encapsulation commands do not have the no form that you're used to on all the commands, where you could simply enter no space and then the command, and it would negate that command like no encapsulation HDLC and turn it off. That doesn't happen. You have to have an encapsulation type, so it simply says we're going to default you to HDLC. If you want something else, just put it in and we'll change that for you automatically. All right, let's look at the diagram down here. We're going to set up a PPP connection from router number 1, as indicated here, to router number 2. It's obviously going to be over a serial link since we're talking about WAN protocols. The network we're dealing with is 192.168.2.0 with a 24-bit mask. Dot 1 is the interface here, dot 2 here, okay? I have the addressing in green, so it's a bit lighter because it's not as important as just the encapsulation that we're going to set up with the configuration on each router. The first router we're going to jump into for configuration is router number 1, as denoted here by the prompt. As you can tell, I'm already in the privilege mode. So what I'm going to do is just get myself into the configuration mode, and then we're going to assign ourselves to an interface, in this case serial 0, and then encapsulation. We can use the short forms of these commands. So encap PPP will get us encapsulation PPP. Now let's go on to the second router. This is router number 2, and do the exact same thing. Configure via terminal, interface, serial 0, encapsulation, PPP. All right. What I want you to notice is that this link changed its state to down for a period of time there. And the reason it did that, and you can see it here, is because the encapsulation on router number 2 was still at the default of HDLC, while the encapsulation on router number 1 was changed to PPP, as we see here. So for a short period of time, we had different types of encapsulations on each end. And obviously that won't let us communicate. Okay, we have to be speaking the same language at each end. Once this was changed to encapsulation PPP on router number 2, our state changed to up here and here. So as you can see, this one command of encapsulation PPP will allow us to connect from router number 1 to router number 2 and sustain traffic. And it does that because it has other variables, but what it does is simply takes the default for each of those actions. So saying that, there is some advanced configuration that can be done. We can change things like the maximum received unit. We can change compression types. We can also choose or choose not to use magic numbers. These are commands that can be used as well, but because we can take the defaults, as soon as we issue this command, we can get up and running between these two routers pretty quickly. If you're not familiar with these variables here for the advanced configuration, don't worry about it. We're going to go over them in detail later in this nugget. All right, don't take my word for it that these two routers are communicating. Let's go back into those devices and show you that they are. I'm going to get on router number 2, and simply we're going to exit the configuration mode, and I'm going to ping the interface of the other router, 192.168.2.1, and there we have it. Now let's go down to the other router and do the exact same thing. Let me get out of configuration mode, and we're going to ping 192.168.2.2. I guess not the exact same thing because we've got to ping a different address. All right, and there you go. So we have connectivity with that basic command structure that we set up with one command. There are 4 components, or phases if you will, in the point-to-point protocol, and they are, starting with the top, link control protocol. These are addressing the layer 2 variables. Then we also have authentication. This is an optional phase. And within this optional phase, you have 2 choices, PAP and CHAP, that we're going to cover in more detail later on in this nugget. We also have the network control protocols. Note that this is protocols, this was protocol. This is one protocol. This is network control protocols. In other words, we're going to have a multiple protocol environment. And these protocols are the layer 3 protocols that are going to be supported. So some examples, IP, IPX can both be supported, and also AppleTalk. So as you define any of these protocols within that serial link that you're establishing connectivity on, and you have PPP running as the encapsulation, NCP is going to establish support for whatever protocol you have set up. And then finally, the fourth phase is encapsulation, where we take the original information that we get from the network layer, bring it down into the data link layer, and encapsulate that packet. Now, I understand that the description of these components alone might leave some people asking, yeah, but what's our goal? What are we building here? So let me give you an analogy to cling to as we go through this discussion. First of all, this mountain here is going to represent router number 1, and this is going to represent router number 2. What we have is a chasm or a gap here between these two routers, and we need connectivity. All right. The first thing we're going to do is the link control protocol is going to pass information between the two to try to establish basic connectivity, if you will. Now, I've denoted link control protocol with this blue dot. Link control protocol can be seen as the first pieces of rope that we string across these mountains to lay the foundation for our bridge. Okay, so we're building a bridge across these two mountains. Okay, then we have the authentication protocol. Simply that is asking from one end, hey, who are you, to make sure that we're building this bridge with the right people. Okay, these are our friends, not our enemies, coming across after we build this, that kind of a thing. That's why it's optional. You may know that already. All right, and then we move into network control protocols. This is the layer 3 information, and this is analogous to the wood slates across that bridge and the handholds, so that we can actually make it across. So when we say we can make it across, we're ready to travel or convey some kind of data across this connection. That's where encapsulation comes in, because it has to be formatted correctly to go across this bridge once we've built it. The job of the link control protocol is to establish, maintain, and terminate links. Okay, and the way it's going to do that is by using 3 different classes of frames. What we see here is the link establishment. As we said, it establishes. Link management, which is used to maintain the link, and then link termination types of frames. Let's talk about the frame up here. Here we have the basic diagram or the basic format of the frame. First, we're going to have a flag, then an address field, a control field, each of these being 1 byte long, a protocol field which is 2 bytes long, LCP data, and then a CRC, which is simply a check to make sure all this maintains its data integrity. So let's look at each field in a little bit more detail. I think you're going to find this interesting. First of all, the flags. It is always the same. This is going to signal the start of this frame. So it's 0, 1, 2, 3, 4, 5, 6 ones, and a 0. Then the address. We really got to think about this, right? This is point-to-point connection. I have a router here, I have a router here, a serial link between the two. Why do I need addressing at this level? I only have 2 ends, right? So because I don't, what they do is this is always coded as 8 ones. All right. Then the control field. The control field is always going to be the same as well. That's going to be 6 zeros, 5, 6, and 2 ones. All right. Now here's where it gets different. The protocol is going to identify the type of information that is held here in this portion of the frame. So the different values for the protocol exist. One for NCP, one for LCP, as we're talking about now, and another one to identify an IP datagram. Okay, so the LCP value that we're looking at now is, and this is the hex value, C021. All right, so if you're ever looking at a protocol analyzer and looking at these packets, if you have a value here of C021, then you know what follows is LCP data. All right, so far we have the classes of the frames, and we also have the breakout of what the frame looks like. Now let's look at the 4 phases of LCP. Keep in mind that on LCP, all we're really doing here is establishing the framework, or those first 2 pieces of rope across the 2 mountains. Okay, we're not doing anything beyond that. The first of the 4 phases is link establishment and configuration negotiation. So we're going to establish connectivity on the data link layer, and we're going to negotiate the different configuration variables. Remember, we talked about the advanced variables, the maximum receive unit, the fact of whether or not we're going to use magic numbers or even the compression. That all happens here. Okay. Then we have link quality determination. That's periodic tests that are going to run through and make sure, for our analogy here, that the strength of these ropes is holding up. In other words, that I have connectivity over my data connection for the network. Then we're also going to allow network layer protocol establishment. In other words, we kind of sit back here and allow the NCP portion to do its job. And then this last phase doesn't really have much to do with our analogy, but it's link termination. Links can be terminated at any time. It's independent of NCP operation here. This LCP can drop whether NCP is ready for that or not, and simply it's going to let the higher layers know, hey, I'm going to drop, it drops, and they do the same. We're going to discuss each of these phases in more detail in the coming slides. So let's start with the first phase. Here we have link establishment and configuration negotiation. Again, the advanced configuration is what we're looking at. So let's start with maximum receive unit. We have both ends, or both points, if you will, on our point-to-point link, and one side telling the other the maximum unit that I can receive is X size. So let's say 1500. All right. This is much like the MTU that we would normally see in IP traffic. Different name, but the same result. Essentially, this is what you can send to me. Okay, this is as much as I can handle. The next thing that we need to look at is the use of magic numbers. Now, exactly how magic numbers works, we're going to cover in the next section because that has to do with the maintenance of the link. But here we're going to decide a yes or no. Simple as that. Yes, you want to use them, or no, you don't. And both endpoints obviously have to agree. One can't try to use a magic number while the other doesn't. All right, and then the last is compression. Now, with compression, we have a couple of choices on the types of compression that we're going to use. And in fact, we can configure the compression here, as you see here, manually. All right, let's talk about compression for a moment. The cost first. If we do compression in a hardware environment, in other words, we add an additional card to our router or our device, then that is a cost of money, of dollars, but really no cost in CPU cycles. For software, it's going to be resident in the device, so we don't have to add anything new to the router, but it is going to cost us CPU cycles. Now that can be important because it can degrade the service of our router to our network. So then you ask, if I've either got to pay money or CPU cycles, why do I want compression? And here's the answer. The link can be either an expensive link, so we have to keep it at a low bandwidth, or there might just not be any room to grow, okay, within your connecting CO. So what you're going to have is, rather than crowding this link with large frames without being compressed, having a longer queue, this memory here serves as a queue. In other words, where packets are stored as they're waiting to be transmitted out on the wire. So you can have a longer queue with longer packets inside of longer frames, and also once you get on the wire, the bandwidth utilization will be high because they are larger frames. So what we can do with compression is make them smaller. I mean, that's really all we're doing is making them smaller so that we have less of a queue and less bandwidth utilization over the wire, and it's at a cost. Given a choice between these two options, you would almost always want to opt for saving money. In fact, too many networks out there throw good money at network problems that could have been fixed with better engineering. So let's talk about the software solution and the CPU utilization. What you want to do is use the show space process command. This is going to show you your CPU utilization, and as long as you don't get above 60% is the recommendation for the Cisco devices in using CPUs, you should be fine. All right, so because we want software as our first option, let's go ahead and get into our routers, and we're going to look at the configuration using these commands of software compression. That's what all three of these are. Here we find router 1 waiting for us and ready. All right, as you can tell, I came in, entered the user mode, got into the privilege mode, issued the configuration command, so now I'm in the configuration menu. Let me jump into an interface. So we're going to go with interface serial 0, and then we opt for our compress command. I'm going to issue the question mark at this point so that I can show you the different options for compression. What we have here is stack, predictor, and MPPC, okay? Stack and predictor are standard software compressions. The note that I want to make on the MPPC is that it has the ability to connect to a Microsoft host via a dial-up connection. So let me show you that here. What I'm going to have is a router, a dial-in connection, and then a host environment here. This could be N1, Nugget 1, that is a Microsoft product. And what this stands for is Microsoft point-to-point compression. All right, so that can be established over this link. Now, not all operating systems, iOS, Cisco operating systems are going to have these options. If I look here in router number 2, again, jump into an interface serial 0, and then opt for my compress command with the question mark, you see that the MPPC is not available. So this actual option became available as of 11.1, that's iOS version 11.1, and it's not available in all revisions since then. So just be aware and make sure you check on your configuration that you have that support if that's what you're looking to configure. So there you have a few examples of the types of configuration negotiation that happen in the first phase of link control protocol. Now let's move on to the second phase, and this has to do with the maintenance or the link quality determination of that specific link. What we're going to study first is called link quality reports, LQR. And what each router is going to do in this one point-to-point link is submit a link quality report to each other. Link quality reports contain the number of packets and bytes that have been received from the other router. So router number one here is going to say, I have received some number of packets, let's say 8, and I have received 1,500 bytes from you. All right, once router number 2 receives that information, it's going to compare that to what it knows it is transmitted out of this interface up to this point in time, and once they make that comparison, they're going to come up with an error percentage value, and that's going to tell you the quality of this link. So in some cases, they may opt for a longer link that goes through some other hop or something of that sort to get to this destination because of the quality across that link, even though it is shorter. Another mechanism that can be used to test the quality of a link is called magic numbers. I told you this would all come together, right? You got to love it when it does that. All right, the use of magic numbers, what it does is it detects loops in the line. So I think what we need to do first is explain exactly how we would get a loop in our line. We've defined this as a point-to-point link with 2 endpoints. But you've got to understand, because it is a dial-type connection, we're dealing with modems on this line as well. And these modems can be placed in loopback. Simply put, what that means is you can have a line transmitting from the router to the modem, from the modem to this modem that's closest to R1, and that modem be in a looped environment to where it will simply loop the traffic back on the receive pair of the modem and the receive pair of the router. Now, this modem does not have to notify that router that it has established a loop. In fact, there's no protocol that makes that happen. So what it does is it uses magic numbers so that it can know that this is happening without the router or the modem telling it. So let's see how that happens. So we have a router here, another router here. We have modems in between. Each router is going to select a magic number that it transmits out, and it will be different than the magic number of the corresponding router on the other end of this link. So it's going to transmit out the magic number periodically of its own. Let's just say this one's 10, and this router, router 2, will do the same. Let's say this one's 20. If at any instance in time this router receives its own magic number back, again with that scenario where it transmits 20, receives 20 at this modem, is linked back, so the 20 is coming back, so the answer it gets here as a magic number is 20. It knows that there is a loop in the line somewhere, okay? And you can program your routers to then drop this link or this LCP establishment once a loop is up. These tests and others like them can be ran periodically on your link to make sure that you have quality LCP connectivity. All right, let's move on to the next phase, and it's this phase here, allow network layer protocol establishment. What we're really doing here is just allowing what we've built so far to be used by the NCP. Remember that I had the support ropes as my LCP in my analogy. Now what NCP wants to do is it wants to develop this bridge, or let's say the wood slats across this bridge so that we can travel across. Now if for some reason that was brought up and at some point all of them broke or all of them tore down for any reason, it could be rebuilt without really affecting what we built on our LCP link, which is these guides or these support ropes. Okay, so the same idea exists within the protocols. LCP can remain established regardless of what happens at the NCP level. These network control protocols, they can come up, they can go down. You remember you have IP, you have IPX available, and you also have AppleTalk. Okay, now each of these is going to have a specific CP. So when you're reading or you see the terminology, you're going to see these referred to as IPCP type of traffic, IPX CP, or AT, short for AppleTalk, CP. All right, so just so you know what they are, and each of these will come up periodically and independently of the LCP. The next phase we have is the link termination. What can cause this LCP to go down? We know that it's independent of NCP, and these are the things. The line itself on those devices that are supporting this, the serial lines, can go down. So if a line goes down, obviously the LCP has to drop as well. There is also an administrative closing that can be programmed in, and that can be done by the administrator. And then the other option is what we just talked about earlier. As we're looking at that quality determination, if we find that there's a loop on the line, the devices can be program to tear down this LCP. So far in this nugget, we saw exactly where PPP stands among all the other WAN protocols. We also looked at the command used for configuration. We saw the components, and there were 4. And then we also saw that there were 3 classes of LCP types of frames, and we also saw that there were 4 phases within LCP. So let me clarify this a little bit further so we don't have any confusion. I have here the 4 components, 1, 2, 3, and 4 of PPP. So the high-level components is LCP, authentication, network control protocols, and then encapsulation. Within LCP, we further defined 4 phases of what's going on to set up, again, with our mountains here, those ropes, those support ropes, across so that we can make our connectivity. So the next PPP component to be covered is authentication. Remember that as far as components go, authentication is optional. But if you do choose to use it, you have 2 choices. The first of which is called Password Authentication Protocol. In short, it's PAP. And the other choice is Challenge Handshake Authentication Protocol, which is short for CHAP. All right, let's explain how they go. Keep an understanding that this CHAP is more complex than PAP is. PAP is going to have a router simply transmit across a combination of a name and a password. This combination, once received by router 2, it was sent by router 1, is going to be verified against the database. And that database can either be local to this router, which would be AAA, which is a form of authentication, authorization, and accounting set up on Cisco routers. So it can be a local database that we match against, or it can be a database on a server like a TACACS or a TACACS Plus server. Simply put, these will reside on some host somewhere with a list of names and passwords, and if the one that was submitted by R1 exists either locally or on the remote database, then we will send back the fact that we have a match, and we're going to proceed now letting our NCP establish its connections, because at this point, this is after the initial LCP connection. We're ready for NCP to do its job. Now, if for some reason that name and password that was supplied by R1 doesn't match on these databases, then we will simply say access is denied, and we're going to tear down the partially set up LCP connection. All right, now let's look into the challenge handshake protocol. The difference here is that we are dealing with encryption. With PAP, when I send this name and password from router 1 to router 2, this is in clear text. It can be viewed by other devices on the network. All right, this is what's going to happen with CHAP. First of all, you have to understand that we're dealing with shared secrets. In other words, within the configuration of each of these routers, there is a secret password that is known to the 2. So what's going to happen is router 1 is going to issue a challenge. You got to love where these protocols and methods get their names, right? So it's going to issue the challenge, and then router 2 is going to receive that challenge. What it's going to do is it's going to encrypt that challenge with this shared secret. And when it does that, it's going to come up with a value. Let's just say that that value is Y. It's going to transmit that value across and back over to router number 1. When router number 1 receives Y, it's going to do the same thing that router 2 did. It's going to take the challenge that it sent across, it kept it here, encrypt it with the shared secret that should be the same as this other router, and come up with a value. If it comes up with the value of Y, it knows that it's talking to router 2 as it's been defined with the shared secret. Okay, and then as we set up here, we'll continue setting up the NCP connections. If for some reason that value comes up to something different than Y, let's say Z, and these don't match, then again, access will be denied, and at that point, we're going to tear down the partially connected or brought up LCP connection. There you have authentication. It's pretty straightforward, and it's recommended on most scenarios where you use it PPP. All right. Now let's go into the network control protocol. Here again we see the frame. Remember, within the frame, the flag field, the address field, and the control field are always going to be the same. And where we're going to find something different is within the protocol field. So when we're dealing with NCP, the value in the protocol field is going to be 8021. Remember that this is a hexadecimal value. So if you want to know the binary breakout to this, it's going to be 1000. 0000, because here we have an 8, here we have a 0, and it's going to be 0010 for the 2, and then 0001 for the 1. Remember this from our binary discussions earlier in this series. And because we have 8021, the information here is going to be NCP data, or Network Control Protocol data. Now, this is the support at the PPP level for network protocols, namely IP, IPX, and AppleTalk. Now, as we configure each of these protocols on that serial link, we're going to have information floating across, and it will be labeled as IPCP, which is IP Control Protocol, IPXCP, which is IPX Control Protocol, and then obviously the ATCP, which is AppleTalk Control Protocol. As we discussed earlier, this isn't something that you have to set up as far as specifically naming in a command. Let's set up IPCP, IPXCP, or ATCP. As soon as you are in configuration mode, identify an interface to configure, and then configure some network level protocol like IP by using the IP address command or IPX with the IPX network command, then this is going to happen automatically. Referring back to our analogy, at this point, we have configured our bridge. We have no data crossing that bridge, but we have everything we need to support that data across. We have the LCP, we have the authentication, the who are you, I am Y, that's who you were supposed to be, thank you very much, and then the NCP, the support for these network protocols. Now what we have to do is move into the encapsulation phase so we can move our data across. Again, we're going to look at our frame. Here we have the flag, the address, and control. They're going to stay exactly the same as we indicated before, and then we're going to have a difference in our protocol. Now the protocol is going to be identified as 0021, okay? And that's going to let us know that what follows is an IP packet. Let's say that this is layer 2. This is where the frame's being built. You've got to picture in your mind layer 3, the IP header with the data coming in, and that's what resides right here, or the IPX information, if you will, if it's IPX that we're encapsulating. More simply stated, we accept the network layer input, in other words, this packet, and we wrap it up in our PPP blanket, which is the header, and then the trailer for transmission over our link, which in this case, in our analogy, is over our bridge between the two mountains, R1 and R2. We started this nugget with an understanding that PPP, as far as its placement within WAN protocols, is in the category of point-to-point along with HDLC. The difference is HDLC only supports same vendor configurations, where PPP you can have multiple vendors. Then we looked at the configuration. We have one command, encapsulation PPP, and that setting allows immediate connectivity because it takes defaults for the other variables within the configuration. We also saw the 4 components of PPP, the link control protocol, the authentication, which was optional, the network control protocol, and then the encapsulation. Then we took a more detailed look at the first component of PPP, which was link control protocol, and understood that it had 4 phases: the link establishment, the link management, NCP support, and then finally link termination. And then with authentication, we had 2 choices, PAP or CHAP. Then as we looked at the network core protocols, we understood that there was support built in for IP, IPX, and AppleTalk. Within encapsulation, we understand that it's the accepting of a packet from the network layer, wrapping it up in a PPP header and trailer for transmission over the link. I hope this has been informative for you, and I'd like to thank you for viewing.